So we've arrived at this equation, and we are predicting that for any given period of time, the amount of charge, the amount of time it takes for any percentage of the charge to drop will be the same for any time period, i.e. we're going to get exponential decay. That's what we're sort of trying to show now. So time to get from Q0 to half of that, if that takes that long, it'll do that. Then to get to half of that with the same amount of time, it'll be there. Then to get to half again, will be the same, etc. And we should get this typical exponential decay curve. So how are we going to do that? What we're going to actually do to test it, to see it? Well, here's what we're going to do. We're going to get 3 cells. You can get as many cells as you want, and set it up. So we have here a 3-way switch, so when the switch is up, it makes a complete circuit there. I think you can see that, and then it will charge this capacitor. When I switch it from there, it breaks this circuit, and as it goes across, I can now run the charge out of the capacitor through a resistor. So on this circuit now, I put a resistor, and then I will run that resistor from the back of there into there. So now what will happen is, I put it in the up position, charge will flow around this way, whoopsie, flow around this way, fill up the capacitor. Okay, if I put it down, it'll run the other way. Okay, I'm sorry I say charge, I say conventional current will flow that way. Obviously it'd be electrons going the other way, but that's besides the point. So in the up position, I'm charging the thing, and in the down position, I'm going to discharge it through the resistor. Now all I need to do now is charge it up, get my multimeter out, get my voltmeter out, and plug my voltmeter in parallel with the capacitor here, So this end's going to go on there, and this end's going to go onto here. And if I've got that the right way around, that'll be a positive value. Now, of course, I do appreciate this looks now like quite a big mess of wires, but as long as you get the take-home message really is that what we're doing here is we're going to look at the potential difference, okay, against time. Now, if we just quickly go back to this graph over here, this of course I've talked about the charge, but as we know, the potential difference on the plates is directly proportional to the charge on the plate. So this is the voltage, the graph of the voltage is the same as the graph of the potential of the charge, and it's the shape of the graph that we're looking for, not anything else. So with that in mind, if we were to do some recording, we'll look at time and the potential difference, and we look at this every 10 seconds or so on, and you'll see what I've got here. We can record the potential difference every 10 seconds, and we can see it. Now if we just take a quick look at this, and I will zoom in on this before I switch it through so you can see it a bit better. When I flick the switch, we'll see the potential difference start to drop, and straight away we see it going off at quite a high rate, and over time, if we keep watching this for a long period of time, we'll see it, the potential difference will drop slower and slower and slower. Now in this particular case, I've got quite a high value resistor, and so for this demo stuff here, it's going to be painfully slow to watch this get down to 0. We're not going to bother doing that. I'm going to switch now straight away to some data that I've got from something we did in the lab, which will show this graph quite clearly.